Today we will answer a simple question. How much does it cost to open a garage door? The question and its solution are simple enough, but what's important here is number 1, understanding the base principles of energy, and number 2, having the problem-solving skills to know where and how to apply these principles. We need these qualities to be successful in physics, engineering, and many other parts of life because we usually won't have some garage door equation that we can plug everything into and solve for us. We need some property which isn't even identified yet, then we need to find a way to bridge the gap between that unknown property and our final answer, which will be some amount of money. I've purposely avoided mentioning any quantities or boundaries for this problem because I would like for you to first try solving this problem on your own by making assumptions and taking, estimating, or looking up your own values for quantities you need. Pause now if you would like to try this on your own beforehand. Now, I'll show you my method. First, we need to outline our process. The answer we want is an amount of money. So why does opening a garage cost money? It takes electricity to run, and electricity costs money. Electricity is usually sold by the kilowatt hour, which is a measurement of energy. So, if we can find how much energy we need to open the garage door, we can then find the cost of the energy. Now we can reframe our question. How much energy does it take to open a garage door? Reframing the question is important because the closer and closer we get to the answer, the clearer and more solvable the questions will become. So again, we work backwards. Why does opening a garage door require energy? The garage door needs to move upward against gravity and friction. We know from the principles of energy that for an object to move upward against gravity, we must give it gravitational potential energy, which will come from the electric motor of the door. The friction will waste some of our energy, but we'll ignore it for now and just look for a baseline value. Once more, we reframe the question. How much gravitational potential energy does it take to open a garage door? Suddenly, this question becomes a lot simpler when we look at the formulation for gravitational potential energy. It's equal to the mass of the door times gravitational acceleration, g, times the change in height of the door. We no longer require deeper digging into the principles. G is a known constant, and the mass and change in height are measurable quantities. Our outlining process is now complete. We'll measure the mass and the change in height for the door, then calculate mg delta h. This energy will be in joules, which we can convert to the standardly used kilowatt hour. Finally, we will find the cost of this energy by multiplying it by the kilowatt hour cost of electricity. Now we can put this into an equation. The energy is mg delta h. Online, I found that a garage door has a mass of around 70 kilograms. For the change in height, remember that this is based off the center of mass of the door. I measured the center of a door to rise approximately 1 meter. To convert it to kilowatt hours, we recognize that a watt is a joule per second. A kilowatt is 1,000 joules per second. So, a kilowatt times a second, or a kilowatt second, equals 1,000 joules. An hour has 60 minutes, each with 60 seconds. So we multiply by 60 squared. So, a kilowatt hour is 1,000 times 60 squared joules. This tells us that to convert from joules to kilowatt hours, we divide by 1,000, then divide by 60 squared. Now that it's converted to kilowatt hours, we can multiply it by the cost per kilowatt hour. This varies, but the average cost in the US is approximately 14 cents per kilowatt hour, so we'll use that. Computing this, I get a value of about 0.003 cents. We must remember that this was ignoring friction and other internal mechanical forces, so our value is an underestimate, but it gets us in the ballpark for what we're looking for. With an understanding of physical principles and equations, and with a little bit of creativity, we can approach this with even more accuracy. For example, what if we used electric measurements or the manufacturer's ratings for the door opener? We can further apply this problem-solving logic to other situations. How much does it cost to boil a pot of water? Or to cook a pizza? Is it cheaper to drive across town for gas that costs 5 cents less? If a solar panel could convert sunlight into cheeseburgers, how long would it take? All of these questions are answerable, but not because you'll find them on an equation sheet or in a book, but because you can understand the logic and physics behind these scenarios.